everyone, welcome to the lecture number 6 of the chapter Light. So far we had lecture 1, 2, 3, 4, 5, which we have dedicated for the reflection and refraction of light. We have discussed the two most important phenomena which are related to the light, the reflection and refraction. What we have discussed in the previous lecture was about the glass slabs and the very important numerical discussion we had in the previous class about the apparent depth and the glass slab. Like in the glass slab we have the lateral shift. Now in this section, in this particular class, I am going to discuss with you about the lenses. So I hope you all have heard about lenses in the lower grades, or even if you are not from the science background, if someone is not from the science background, he must have heard of the term lenses. And when we use this term, if someone's eyesight is weak, if someone is having difficulty in reading a book, or if someone is not able to see the things which are far away from you, so that time we go to an optician and then he suggests us to use a lens, right? So inside that glass we have a lens. So how does it decide which lens I have to put for this person, how which lens I have to put that person? So that would be our discussion in the next chapter, human eye and colorful world. So that would be the lecture number 3 and 4. But in this particular session, first of all, I'm going to give you the basic idea about the lenses. How does they work exactly? Then later on in the next chapter, you would be getting the idea that how to use them. Now, how to apply them in our day-to-day life whenever we need it. So that is the basic part which I'm going to discuss with you in today's class about the lenses. So what is a lens? How do we see the image from the lens? So for that, let me show you the screen. So just give me a second. Okay, so I hope you are able to see my screen now. Now, for the lenses in this particular session and in this particular class, I am going to discuss with you the refraction of a light ray by a spherical lens. Then we will be discussing image formed by the spherical lens, image formation. And then I'm going to discuss with you a very important formula called the lens formula. And in the end, we'll talk about the magnification in lens, right? Okay, so now let us begin. First of all, with the lens. So what is a lens? So if I just talk about the lenses, then if you take a homogeneous medium, homogeneous means it's same everywhere, right? Okay. And if you take a homogeneous medium surrounded by two curved surface, so suppose we have this one curved surface and this is the another curved surface, and now you have filled this curved surface. Inside this we have another material, then this will be a lens. So basically a lens is a homogeneous medium surrounded by two curved surface. Now it is not only necessary that it has to be both side curved. More technically, I would say at least one side should be curved. In general, in our grade 10 level, at our grade 10 level, we'll be getting the both side curved. So based on that, we have two types of lenses. So first is the convex lens. So that's the convex lens. And other one is the concave lens. Now we can also frame one of the surface curved and one surface is planar. So that is also a lens. Suppose this one. Now this is also a lens. It is called plano-convex lens. One side is plane. And similarly, you guys can make a plano-concave lens as well. So this will be the plano-concave lens. Okay. So, but you don't need to get confused. In our syllabus, in the grade 10 level, we'll be getting the convex lens and concave lens. So plano and all this you will be getting in the grade 12 if you go for science. Okay. Now, I'm going to discuss with you first of all the ray for image formation with the help of these lenses. All right. And when we talk about the rays formation, image formation from the lenses, then first of all, let me show you the basic ray diagram for a convex lens. So if I talk about the convex lens, then how would the basic ray diagram look like? Okay. So Again, I'm going to use a very simple thing, the laws of refraction. And based on that, we will be seeing what is the nature of this convex lens. So suppose we have the convex lens kept over here. Okay. And that's the principal axis. And now in the case of mirrors, some terms would be similar here. Exactly what we have done in the mirrors, the similarly we'll be having in the lenses also. So first of all, if I talk about few terminologies, then this center part is called the optical center. Oh, so this is called the optical center. Optical center. And then apart from this, focus is there, center of curvature is there. I hope you have got the idea about focus now. So when light rays are coming parallel, the place where they will meet after the refraction here in this case would be called the focus. So focus definition remains same. Either it is a lens or it is a mirror. All right. So now let us first of all talk about the lens in this case, and we will discuss the image formation. So let me take the object kept at a certain place here on the principal axis. Let's say the object is kept over here at this place. So if object is kept at this place, then what will happen? If I talk about that, then first of all, I'll take one light ray and refraction will take place at the one end. So one by one, refraction I'll be taking. So there are basically two curved surfaces. This is curved surface 1 and that is curved surface number 2. So first I will take refraction through the curved surface 1 and then I'll take image formed by the curved surface 1 as an object for curved surface 2. Let me repeat. This object will be acting like, let me mark it as object. Yeah. This object will be acting like, this will be acting as an object for the curved surface 1. And then the curved surface number 1 will be forming the image, and that image will be acting as an object for the curved surface 2, and then we'll make the image. Okay, simple laws of refraction. Mu1 sine I is equal to mu2 sine R, and we must know how to draw a normal now. In the case of curved surfaces, how do we draw the normal? So suppose that's the center of curvature of the lens of the curved surface. So suppose if you want to draw the normal here, then you just have to join this line. Or if somebody wants to draw the normal at this place, then let's say this is the center of curvature, join them by a line. So at a particular point on the curved surface, you are supposed to join through the center of curvature. And that's how we get the normal line. Okay, so now let us take the first light ray. Its center of curvature will be somewhere at this place. So let me draw the normal. That's the normal. That is the center of curvature for the first curved surface. And now how would the light ray bend? It's a rarer medium and the lens medium is denser. So now light ray would bend towards the normal because it is going from rarer to denser. So let me bend it towards the normal. So see here, it will be bending towards the normal. It's a very small space here, so you should see it carefully. Now at the second surface, what will happen? At the second surface again, guys, you can see here, at this place, if I want to draw the normal, then what I will be doing, I'll be marking this as a center, and then this is the normal line. Now, if this is the normal line, what I should do? Now light ray is going denser to rarer. So basically away from the normal, it must bend. So that blue light must be bending away from the normal. So that is the normal right now. So how it would bend away from the normal? Very simple. It will be bending like this. So basically this was the object location and this is the image location. So that's why if you have heard of it in the lower grades as well, that the convex lens is converging in the nature. If light rays are coming like this, it will make them like this. So it will converge them. So second light ray, to take the intersection, you can take straight. It will go straight without any bending because it is falling normally on the curved surface. Right. I hope you have got the simple idea. Similarly, I will give you as an homework for concave lens. For concave lens, you use the same approach which I did here. I took the reflection step by step, one surface, second surface, and then in the end I showed you that it's acting as a converging nature. So convex lens is converging in the nature. Similarly, let's talk about the concave lens. If I talk in the case of concave lens, then this concave lens, you should do it yourself. I'm just telling you how it would look like in the end. So light rays which are coming, okay, suppose if somebody takes the parallel light rays, the light rays which will be coming here will be like this, and now it would diverge them. It would be acting as a diverging lens. Why I'm saying this? That's up to you. Prove it exactly the same way. Band the light rays. So basically, guys, if you know the simple laws of refraction, you can learn about the lenses without even going ahead, because that's the basic theory behind everything. So you don't need to do any kind of rectification, I would say. You can simply just draw the ray diagram, and you can find out by using the simple laws of refraction. But yes, to make our life simple, I'll be giving you some formulas for the image formation and all. But if you do not want to remember any formulas, you can always go for the ray diagram. But it's your choice, and I hope everyone would agree that we want to remember the formula because that's a fast approach. Okay, so let me go to the fast approach. But before that, as we have recommended you earlier also, that you should remember the ray diagrams, that if this is the object location, this will be the image formation in the case of concave mirrors and the convex mirrors. Similarly, I would recommend you here to remember the lenses part also, that how the image will be getting formed, where it will be getting formed, whether it will be magnified or diminished, that also you should remember in these cases also. So let's discuss about that now, the different ray formation cases for the spherical lenses. So let us begin with the convex lens first of all. Okay, so all these cases I'm going to show you in the next slide now with the ray diagram. Okay, and that ray diagram you should try once after this session yourself without looking at the textbook. So the first case for the convex lens, when light rays are coming from infinity. So when light rays are coming from infinity, from where they would pass? They will pass from the focus, because that's the definition of focus, the place where they'll converge. That is called the focus. So as I told you, convex lens is converging in the nature. So light rays will be converging there. So this place is called the focus. So that is the focus for the convex lens. All right. And now if you remember the sign convention for the convex mirrors and concave mirrors, the same sign convention we must follow here also. What does the sign convention tells you? That in the direction of incident ray, we have to take positive. So this would be taken as positive and this would be taken as negative. And that's why we usually says that convex lenses has the positive focal length. But let me not confuse you. It is not always true. It is only true when outside medium is rarer. If outside medium you take denser with respect to lens, it would not be true. But in your grade 10, 99.99% cases, you will be taking the convex lens focal length as positive only. The reason being because outside medium is rarer always. Rarer, or you can say air only in most of the cases. That's why you don't need to worry about it. So focal length is positive here. Just remember that. Second case, if I keep the object in between center and infinity, so beyond 2f, which you call. So when you keep the light rays, when you keep the object between 2f and center of curvature, now I will be using two light rays here. One ray I'll take straight, and that must pass to the focus. So that's the first ray you can see here. Second ray I would take from the optical center. If somebody wants, they can take through the uh, center also. But I am taking from the optical center because that is most common and more easy as well. So light ray which will pass through the optical center, it will go straight. It will go straight. Okay. So this light ray is going straight. And the place where this refracted light ray 1 and refracted light ray 2 are intersecting, that would be the image. So in the first case, and sorry, in the second case, you can see the image is inverted, as well as it is smaller in the size, right? Okay. And also we can say, oh sorry, yeah, it's smaller in the size. So now let us compare the same thing with the table here. So when the object is at infinity, focus, then highly diminished, point sized image, and real image, and inverted it was. When the object is beyond 2f, it is between f and 2f on the other side. Just like try to compare it. In the case of concave mirror also, when the object was beyond 2f, right, then image was getting formed between focus and center. So yeah, one more suggestion, if you want to do the comparative analysis here, then you would find that the rays of lenses, in the case of lenses and mirrors, they are just opposite, almost. Convex behaving like a concave mirror, convex lens behave like a concave mirror, and concave mirror behave like a concave lens, and the concave lens behave like the convex mirror. So it's quite opposite. Now image was diminished, real, and inverted. Third case, if I keep the object at center itself. So as you remember this, if you keep the light rays at center, the image will be formed at the center on the other side. So this is 2f, this is 2f. So image is being formed here only. And image will be of the same size. Again, I have taken the two light rays parallel and passing through the optical center. That's it. Now the third one. Third one is the case when object is kept between f and 2f on the left side. So when we take the case f and 2f on the left side, image will be formed beyond 2f. And yes, of course, if you remember the concave mirror, because it's a convex lens just like the concave mirror. So when we used to keep the object between f and 2f, the image used to form away from 2f, away from center. So here also it is away from center, highly so enlarged image is coming, real is coming, inverted is coming. Okay. And now if you keep at the focus, then what will happen? Light rays will become like this and optical center will be like this. So image will be formed at infinity, because that is vice versa true. For object at focus, image at infinity. Object at infinity, image at focus. So vice versa is true. Now in the end, when we take the last case, so that's case number 4 we have taken. Now when you take the last case, when object is kept between focus and optical center, so where is the image formed? So now you remember the concave mirror, what was happening there? When object was kept between pole and the focus, what was happening is the image which was getting formed was enlarged, and at the same time it was a virtual image, and erect image was this. So exactly same thing would happen here. So one light ray you will take straight, it will go like this one. Second light ray you would take up from the optical center, but these two light rays will never meet on the right side of the lens. So you will take their forceful intersection. So you will extrapolate them in the backward side, and you will get the intersection at this place. So A prime, B prime, that's the image. So image is beyond 2f, and also it is enlarged, virtual, and erect. Okay. So that is the image formation by the spherical lenses. I hope you have understood all the cases. Now what you must do, you should draw them around 3 to 4 times. For the first time you can take the help from notebook, from these notes. Second time you try to draw them yourself, because that's gonna help you in the exam. And then in the third or fourth time it should be the perfection for you. Okay. Now coming for the concave lenses, exactly in the similar way. So when object is at infinity, image will be formed at focus and highly diminished point size image. So concave lenses are diverging in the nature. So when you take the parallel light rays, so they will diverge like this. So they will diverge, they are diverging like this. So they will not meet anywhere actually on the right side. So forceful intersection I'll be taking, and that will be happening at this place. Okay. And that's what we call the focus. So now the focus is coming on the left side. And by the sign convention also you can say this is the negative focal length. So diverging nature. diverging nature, and the focal length is coming out to be negative. Now, the second part, which is about the formation of a ray diagram with the help of when the object is kept in between infinity and optical center. So in that case, what is happening? Let's suppose I have kept the object between f and 2f. So now it's a concave lens. So concave lens is like a convex mirror. All right. So there also, you, if you remember, we were getting the virtual images, okay, and images were erect only. So similarly, you can see the images are erect here also. Okay. So now when I talk about this, the image will be virtual again, right? Okay. So let's have a look. First light ray you would take this way. It would go diverged. Second light ray we can take from the optical center, which will pass straight from the optical center. This light ray and this light ray will never meet each other. So forceful intersection I'll take, and that will be behind this lens on the left side. And that is happening at this place. So that's the image formation. So image which we are getting is virtual and erect only and diminished in the size. So guys, that's all about the concave and convex lenses. It's very simple because now everything is relatable. Everything you can do yourself now. Concave lenses is like a convex mirror. Convex lens is like a concave mirror. So take that same analogy and try to draw the ray diagrams. Just remember the thumb rule that we can take these many rays. Ray parallel to principal axis will pass through focus after the refraction. Second thumb rule is the ray which will pass through the optical center will go straight without any bending. And the third ray, though it is rarely we will need from the center of curvature if you need. Okay. And also remember that convex lens is converging and concave lens is diverging. So these are the 4 points which we can remember, and we will be able to draw all the rays, all the images formation with the help of convex and concave lenses. Now I'll come to the numerical part of this. So when I come to the numerical part of this, then similarly as we had the mirror formula there, which we also call the mirror equation. So in the mirror equation, if you remember, I told you that 1 by v plus 1 by u is equals to the 1 by f. Similarly, in the case of lenses also, we do have a formula which would be making your life simple. So you don't need to draw the ray diagram every time and then you need to find out. You can find out the numerical distance also, but for the cross verification to make sure, we can go back to the ray diagrams. So ray diagrams are important. At the same time, this lens formula is important. So what does it tell you? That if object is kept AB on this side at a distance u, then 1 by v is the image distance. You can see here the object is kept beyond 2f, so image will be in between f and 2f. 1 by v minus 1 by u must be equal to 1 by f, where f is the focal length of the lens. That's the focal length. So that's how, guys, we will be using it, the lens formula. Sign convention is important. You must use this lens formula with the proper sign convention, because if you forget the sign convention, then you should also forget the marks, because sign convention is the most crucial thing here. If we don't use a sign convention, definitely I can give you guarantee that you're going to lose the marks. It's not like simply for everything you're putting positive. You have to make sure that if light rays are going towards right side, then right side is taken as positive, and if light rays are going toward left side, then left side is taken as positive. So if light rays are, like in this case, the light ray would go right side, so this will be taken as positive, right side of the lens, and hence automatically this would become negative. So that's how we have to use the sign convention. Okay, now let me uh, explain you how do we use this through a question. And before that, let us also talk about one more thing. See, everything is relatable here. As I said you in the previous lecture, that magnification of a mirror. So how do we define magnification? It was height of image divided by height of object. The magnification formula is always same. This is the meaning of a magnification. This is the definition of magnification. Height of image upon height of object. Oh, sorry. It's object. Yeah. So if somebody says that the magnification is 3, that means what I should understand from it? I should understand that if magnification is coming out to be 3, this means that image is 3 times magnified. If object height is 2 centimeter, then image will be of 6 centimeter. And plus sign is representing that it would be erect. So if object is kept like this, image will be magnified and same, erect. Okay. If somebody tells you that magnification is -3, what you should understand from it? That image is again magnified 3 times, but this time if this is the object, then image will be inverted. So that's what the magnification in the magnification negative sign is representing. So guys, in front of you, you have the object kept of the size h, and that's a convex lens. And which case is this? Try to figure it out. In which case we get the virtual image. So that must be the case when object is kept between pole and focus. So let's go back here. You remember this case? Object is kept between optical center and focus. So image was getting virtual. That is the only case where we are getting the virtual image in the case of lenses. Now, if I talk about this, then what will happen? What will be the relation between height of image, which is h prime, divided by height of object, which is h. So magnification is equal to h prime over h. In the case of lens mirrors, it was minus v by u. Here it is plus v by u. So in the case of mirrors, it was minus v by u, and here it is just plus v by u. That is the only difference here. All right. So that's called the magnification of a lens. Okay. So if any lens we are using, and if you want to find out that how much magnified image it will be forming, so that would depend where you have kept the object. Okay, because the u is there in the formula, and depending on that, it will be giving you the magnification. Now let us try to use it in a question. Okay. At what distance should an object be placed from a convex lens of focal length 18 centimeter to obtain an image at 24 centimeter on the other side? So focal length is given 18, and magnification they have asked in the question. So that's a convex lens. Okay. And where should we keep the object? We don't know. Somewhere here. Let's assume that this is u, and that u would be negative now, right? Okay. And where is the image getting formed? So image is getting formed on the other side at 24 centimeter. Okay. We have been asked what is the magnification produced. So for magnification, I need v by u. I don't know height of image and height of objects here, so I would not go for it. I would go for v by u formula. So 1 by v minus 1 by u. Remember, there is a negative sign in the lens formula, is equal to 1 by f. So 1 by v. V is given to us. So how you can put the number there for v? V is nothing but how much, guys? It is plus 24, because it's on the right hand side. This would be positive, this would be negative, because light rays would go right side. So in the light rays are going to the right side, then right side of the lens will be taken as positive. Minus, what about u? So u is negative in this case. So let me take it as minus u. Left side is equal to 1 by f. So focal length would be positive because focus is on this side. So focal length is positive for convex lens, 18 centimeter. Now what else? Nothing. Just solve the equation and get the answer. 1 by u is equal to 1 by 18 minus 1 by 24. And let us just solve it now. Taking LCM 6, taking the common 6, 1 by 3 minus 1 by 4, and which would be giving you 1 by u equal to 1 by 6, 4 minus 3, 1 over 12. So that would give me u is equal to 72 centimeter. So means this u will be equal to 72 centimeter, right? And I should have got it also. Can you think about it? Why this I should have got? It's like you should compare it with the ray diagram. If image is being formed between optical center and focus, because sorry, image object is kept between f and 2f, because the f is at 18 and 2f is at 36, so object is kept somewhere in between them. So if object is kept somewhere in between them, now what should happen? So image will be formed like this. Okay, it looks the enlarged image. Just a second. Yeah. So image is this. And that should have happened also, guys. Why? Because object is kept between f and 2f. When object is kept between f and 2f, then image is being formed beyond 2f. Oh, sorry. When image is being formed between f and 2f, then object must be kept beyond 2f on the left side. So this is the 2f and this is the f. I think I said opposite in the previous statement. What I'm saying, if image is being formed between f and 2f, then object must be kept beyond 2f. Beyond 2f means beyond 36 centimeter in this case. So if you are getting a case of such type, and if you see 4 options available there, then if all the options are below 36 and only one option is let's say 40 or 72 is given, so you can always click that, because you don't need to solve it now. So many times this has happened also. You don't need to solve the question without even looking at the question. If it is a single answer correct, like you just have to tick mark, then you can simply solve it. Yeah, if it is a board's exam, then you must write the entire explanation. Okay, so magnification produced will be how much? V over U. Now V is how much, guys? In this case, the V is given as 24 and U is given as 72. So that would give us the magnification 1 by 3. So image is coming diminished, all right? And yeah, the U was negative here. So minus 1 by 3, and it is inverted also. So it is according to our case which we have discussed in the previous topic. Now going ahead with the next question. What this question says, the image of an object is placed at 60 centimeters in front of a lens is obtained on a screen at a distance of 125 centimeters from it. Suppose you have the lens here, and on the other side you have the screen. So that's the screen, and that's the lens. Okay. So object is kept 60 centimeters away from it. I guess many of you must have guessed it by now which lens it would be, convex or concave. So think about it. In the end, we should compare the answer. This is 60 centimeter and image is being formed on the other side 20 centimeter. Okay. So let us use the formula 1 by V minus 1 by U is equal to 1 by F. Negative sign. V should be plus 120 because light ray would go on the right side. So this is positive, this is a negative. U must be minus 60 is equal to 1 by F. So now what answer you are getting, guys? You are getting 1 by 20 plus 1 by 60 is equal to 1 by F. And that would give us 1 by 60 common. So half plus 1, which will make equal to 1 by F. So I can say simply that half 1 by F is equal to what? This term is 3 by 2, 3 by 2 and multiply 60 is there. So 3 by 120. and that would give us focal length is equal to 40 centimeter, and that too is a positive answer. So positive answer means this length is convex. So now, if you remember, then it was a real image. On the right side, it was being formed, so it must be a convex lens. What would be the height of image if object height is 5 centimeter? Now that's quite simple. Hi upon ho is equal to v over u. Just put the numbers here. That's it. How much would be the v? So v is plus 120. How much is the u? It's minus 60. So magnification we are getting as minus 2. Hi upon ho. So what will be the height of image? It will be minus 10 centimeter. So image is real, it's inverted, and at the same time it is enlarged. So which case was this? The case was when object is kept between focus and center of curvature. So F and 2F. So F and 2F, this was the case. This was the object location. So image must be formed between beyond 2F. And here we can see the image we are getting at 120 centimeter. So this is the F and this is the 2F at 80 centimeter. So yes, we are right. Image is being formed on the right hand side at a location 120 centimeter. Okay, so I hope I'm clear now. Okay, and what about the image? It is enlarged. Yes, it should be enlarged. And it is inverted. Yes, it is inverted. Okay, so that's all about the lenses, guys. So I guess you have understood now what are the lenses, how to use the lens formula, and how to use a sign convention. That is even more important. So in the end, I would just say that focus your complete attention on the ray diagram first of all, and then you must go for the lens formula questions, numericals, because you should be relating at the initial stages when you do the homework from the module, or if you do the homework from the NCRT or from your school textbook, anything whatever it is, you must always see the ray diagram first of all. Then it would give you the confidence that you will be able to match the answers as well. Okay then, so that's all for this session, guys. Thank you so much, and if you get any confusion, if you get any doubt, just put it over the PDF. So thanks a lot. Bye bye. Enjoy.